There.
Hi. Can you sign it?
Yeah. Thanks.
Sure. Yeah, so these are the review sessions for MMAE200. From now on, I guess I have to come up with 3 problems and put them on board, so I'm still setting up a bit here.
Yeah, no problem.
But,
Still not memorized my number. I bet you next week there'll be a bunch of folks in here.
yeah, I hope. I haven't been getting many people.
Yeah, it's strange for that kind of a class.
Did you have any specific questions you want me to go over?
Yeah, I actually have trouble with moments.
Moments?
Yeah, moments are the one that really confuse me.
Okay.
So in these cases, we kind of have everything in. You'll have like forces, and you have then your like vectors or whatever, and then you'll have moments because you can do some on the ground, a pin or a roll, right?
Right.
It's I think it's figuring out where the pick one and then just like how to solve it. I think I just didn't get the idea when we were going over it in class. So.
Okay, well, let's see. I'm going to see if there were any problems you did in class that I could do here.
Yeah, the second problem set I think I had the most trouble with on moments.
Okay. Well, if you have an example problem, I can do that. Otherwise, let's see. I have one right here that we can go over. This was pretty similar to this case. This was, I think he did this yesterday.
In class.
Yeah, I don't do everything the same exact way he does it, so it might be useful for you to see different ways to do it.
Okay, makes sense.
So basically, we've got a beam, a simply supported beam that's being loaded with a 600 Newton force at a 45 degree angle and a 200 Newton force, just straight down.
Right.
Let's see, and then we had another one that was right here, 100 Newtons, and then we're given measurements for. Oh, we're also told that the distance between this pin and the top is 22 meters. Okay. This one was 2 meters distance. Sorry if this is not drawn well, but the distance here from this force to there is 3 meters. And then we have another 2 meters here. Okay, so let me just go on to the next slide to start the free body diagram. Okay, so we just draw the beam, we don't draw any supports. The supports are replaced by forces. So this side I'm going to call side A.
Sure.
And this is side B.
So is that pretty useful to do that?
Yeah.
So like when you're looking at a beam to break it down on the sides?
Right, yeah. It's just, wherever you have reaction forces, it's usually, in my opinion, good to just write a letter or a number there, and then to write the direction that the force is going in.
Okay.
That just is a good way of keeping track of your forces. So then on the other side, we had a pin support, so that's going to give us two reactions here. We have force.
Hi.
Can you sign in?
Yeah.
Okay.
Pins have two, right?
Yeah, pins have two reaction forces in two dimensions. So then we have force dx. And again, this is going to be, we're assuming based on the way we drew it, that this dimension here is from this pin, so that force is acting at that pin.
Yeah.
So if we wanted to take a moment about the pin, we know that it's going the X force here is going to be 0.2 meters away. So, okay. So then we have our other forces here. 100 newtons, 200 newtons here, and 600 newtons going over the degree. Okay, so the first thing I would say it's a good idea to do is to break this down into X and Y components. So you can just do that by sort of drawing it like it's a triangle. So this is the 600, and then here we have a 45-degree angle, and then this is going to be the X component, that's going to be the Y component. So we can say this is 600, and because it's at the same side as the 45, we can say it's cosine 45, and this would be 600 sine 45. And then you also have to take into the relative direction. It's pointing down and to the right, so we know the Y component is going to be negative, and the X component is going to be positive. That's based off of, I drew some components here.
Yeah, now I see your X line.
Okay, so that's that part, and then, let's see. Okay, so I'm going to do this one as taking these as vectors. So this can also be written out as just, let's see, take the force and then do the component vector in that direction, which is cosine 45 in the X direction, so that's I minus, because it's negative in the Y, we say it's minus sine 45 in the J. Okay, so that's that force. So when we do the sum of the forces here, some of the forces, and we're doing the forces as vectors, we're going to say that's equal to the 0 vector. Okay, so this is force A, Y in the J hat direction, plus 600, and it's that one again, 600 cosine 45 I hat sine 45 J hat. Okay, minus 100 J hat minus 200 J hat minus FBX and I hat plus FBY in the J hat. Okay, and so this is actually giving us two equations because we have components in the I direction and J direction. So if you take like components, then you'll get two separate equations. So actually, if you look in the X direction, we just have FBX and then this 600 cosine 45. So those are the only two in that direction. So if you take out the I components, you get force dx is equal to 424.264 newtons. And if you look in the y direction, you're going to get sort of a big equation. Well, it's not too big. It simplifies down to FAY plus FBY is equal to cosine, sorry, 600 sine sine 45 plus 100 plus 200. Okay, and that's equal, this whole right side here just turns out to be 724.264 newtons. Okay, and then now here's a moment part. I think in class he just sort of, he doesn't really do it as vectors because in 2D problems it's all going to be in the k direction because you don't really have, you can't turn it that way and you can't turn it, the only direction you can turn it is out of the board essentially. So, but here it's nice to take it as a vector just to understand where all these directions are coming from. So we're going to do the sum of the moments about pin B, and let's see. So here again, because we're taking it about point B, all of our direction vectors are going to be in the negative I direction, except for the one that's in the from the x component of this, which is going to be in the positive j direction. So our first force here is 100, so we can say that's 2 meters from pin B, so that's negative 2 I hat. And then we're crossing that with, it's a negative 100 force in the j hat direction. Okay, and we're going to add. Okay, now the next force, because we're taking about this point, all of these forces are canceled out because they're through that pin. But this force, since we're saying that it's 0.2 meters above there, that's still going to affect it. So for that, the R value we can just say is negative 5 I hat because this was 5 meters, and then plus 0.2 j hat. And then cross that with this value here. 600 cosine 45 I hat minus sine 45 j hat. Now this may seem like a little bit more of a confusing way of doing it, but if you have a lot of forces and acting in a bunch of different directions, it's actually going to make it a lot easier to ensure that you don't mess up any signs or anything like that.
Yeah.
So then, let's see, and then the last one, we have the force A and the Y was 7 meters away. So we're going to say minus 7 I hat times across F A Y J hat. Okay. So all of these are going to be in the K direction, so we don't need to worry about writing the, like when we're doing I cross J, we don't need to write K necessarily because all of them are going to be in the K. But you do have to pay attention. For example, here we're going to have a J cross an I, and so that's actually going to give you the negative value of that. Do you guys remember about doing like I cross J versus J cross I? Why those are? Okay, well, just like one easy way to remember it from
Versus this.
what?
I always go like this versus this.
Okay, well, here's one way that I try to, like, you can just write it at the top. Well, I'm getting, sorry, hold on one second. This thing is So, one easy way that you can just write sort of at the top of your test. See, it might be a marker or something.
Just that corner of the words and stuff.
Okay.
Try the bottom right corner.
Yeah, I can try that. I guess. Huh, yeah, that's weird. It is just that corner. Maybe the projector's off or something.
Yeah.
Okay, so as a triangle where you list these, you list them in order, I, J, K, in a clockwise direction, and the arrows go clockwise as well. And so when you're multiplying in this, or when you're doing a cross product in this direction, if you're going with the arrows, then it's going to be a positive of the other term. If you're going against the arrows, then it's going to be a negative of the other term. So I cross J would be positive K, whereas J cross I, going against the arrow, will give you a negative K. So that's just one way you can easily write that at like the top of your test or something, and you shouldn't have any trouble figuring it out. So here we have the I cross J that's going to give us a positive K, so we can just neglect the K because it's all going to be in the K direction. We have 200, and then, okay, so here it's sort of a, you have to multiply each part by each part, but obviously I cross I will give you 0 and J cross J. So you have to multiply the I by the J and then the J by the I. So just do it one step at a time. -5 times 600 cosine 40, or sorry, -5 times 600 times negative sine 45. And that's in the positive K hat because it's I cross J. We have, let's see, -3,000, but that negative cancels out here, so we have 3,000 sine 45. Yeah, that's right. Okay. Plus 3,000 sine 45. Okay, and then do the same thing here. We have 0.2 times 600 times cosine 45, but it's J cross I, which is going to be a negative value. So we have minus 120 cosine 45. Okay, and then the last term, this just becomes a K, so it's -7 FAY. Okay, so now that's equal to 0, which gives us FAY. And then, let's see, we had an equation before with FAY and FBY. So if you plug FAY into that, subtract that from this side, you end up with FBY is equal to 404.765. Okay, so any questions about this?
Yeah, I think whenever I use sort of quicker way, I kind of forget what's going on in the background.
Yeah, I mean, it would in a quicker way if you have,
Test for time.
yeah, and if you have it, if like everything's, it gets confusing when you start dealing with moments in multiple directions. And I mean, once you get up to higher level classes, you're going to need to do it the vector way because you're not just going to have a moment in the K, you're going to have it in the X, or in the J and the,
Yeah.
yeah, so, I mean, it's definitely possible, like, it's just, I don't know if it's really worth it if you're confused about the signs to do it without, looking at the vectors. I mean, of course, it's possible to, do it like this, say, oh, it's, this is the positive K, that's the negative K. It's, I mean, for simpler problems, that's good, but for complex problems, it can get confusing. So let's see. I made another problem here. So this one's just going to be a simply supported beam, but this time it has a moment at, we'll just say, let me put put some dimensions on here. So this is 6 meters, and this is halfway through. This is 3 meters. Okay. So normally when you're dealing with simply supported beams, you can't have a force acting up. But because it's acting at the pin, it's not actually creating a moment about this pin, and that's allowing us to put a force there, even though normally you can't have one acting up.
That makes sense.
So let's do a free body diagram here. Okay. I'm just going to try to do this again. See if I can get this to work better.
That's for the color breaks.
I don't know why it's so loud. Whoops, what happened? Okay, that's fine. Okay. So, then we have a bar, simply supported. So here, it's going to be, we'll call this pin A and the roller B. This is force A and Y, and then force A and the X. Okay, and then we add force going down here. Let's just see what the value is. It was 100. Oh, it's going up. 100 newtons up. Okay, and then this, we have a roller here, so there's only one support going positive direction. And then we had a moment midway through, it's 50 newton meters. Okay. And that's going to be in the negative K direction. Okay, so first thing, this time I won't do the vectors because they're all going in either the X or the Y, so it's easier just to do it. As the sum of the forces in the X is equal to just FAX, and that's equal to 0. The sum of the forces in the Y is equal to FAY plus 100 plus FBY, and that's equal to 0. And then we can take the sum of the moments about basically any point. Now with a moment like this, this is occurring at any point on the beam. I mean, it's occurring at this point, but if you're taking a moment about this point, this is still added to it regardless of where you're at. So if we do some of the moments about point A, that's probably the best point to take it about because you have 3 forces acting there. So that should give you force B, hopefully. So let's see, some of the moments about A. We have the, this would be in the negative K direction, so it's just negative 50 newton meters. And then plus FBY, that's going to be in the positive K. And we said the length was 6 meters. So that just gives you FBY is equal to, that would be 50 over 6, sorry. This is equal to 0, 50 over 6. and then we just plug that into here to get FAY. So FAY, okay, is equal to 100 minus 50 over 6. Not sure what that is off the top of my head, but so that's that problem. You said you had a problem off of one of the problem sets?
No, I actually was pretty good with the trait problem too.
Oh,
That
okay.
was probably the worst ever problem too.
Do you have any questions?
Oh, no, not really.
Okay.
Wait, can you go back to the,
Sure, which slide?
yeah, this one. How do you know that the moment arm for FDY is 6 meters?
I think I put it in the problem. Let's see, yeah. So I said, sorry, I didn't draw this very well. This is the entire length is going to be 6 meters, and I said the moment was occurring 3 meters away. Actually, in the problem, it doesn't matter where the moment occurred in this example because it's acting, if you're taking the moment about this point, it's still going to be negative 50, or this point. It doesn't matter what the moment arm is because that is a moment itself. But the force here was acting 6 meters away from the pin at A.
I have a question there. How did you get 100? It was 50 over 6. Or no, go back a second. The screen you were just on. For force of AY, shouldn't it be like minus 100 minus 50 over 6?
Let's see, force AY.
It's force AY plus 100 plus.
Yeah, I think that must do it. So yeah, you're right. And that makes sense if you're.
Because it's negative K, right?
Yeah. It also makes sense if you're just looking at it as a whole. If there's a force acting up there, this pin has to be pulling down, and also this moment is causing that side to rise up. So it makes sense that that would be negative. So it'd be going downward. So that would be negative 100 minus.
It is almost like a tension force then, preventing it from going up.
Yeah, kind of. And that's sort of one of the things about roller pins that you have to be careful with. If you're doing a problem and somehow you get that the reaction at the roller pin is down, that could be a problem because technically roller pins only support positive. Their reaction is only up. It's never going to be down. So you got to be careful with that. But pin supports can support in the positive or negative. It's just not going to. Basically, it's going to say that it can't translate at all. Whereas the roller, it still can translate. It's just it can't go down. So let's see. Let me just slide here. Let's put up the third problem. So I'm going to go over, there were some problems he did talking about whether some setup was statically determinant or statically indeterminate. So let's go through a problem like that, but actually solve for some things. Let's see. Okay, so there's one, we have a wide beam like this. And a pin here. And a roller over here. So let's just add some values to the lengths here and then some forces. So let's see. Let's say we have let's see, how do we want to do this? Let's say 100 newtons here. And let's try like 50 newtons here. Okay, and then let's say this is 5 meters, and this is 3 meters. So that's the length of each of those sides. So the first thing we're going to do is write a free body diagram. Let me just write this down for a second. Oh yeah, I guess I should probably write where the force is acting. So we'll say this is 1 meter. And then we're going to say that that's just acting at the corner there. So draw the entire beam free body diagram. Okay, so at the pin here, we have force going this way. We'll just call this point A, and then this is point B. Okay, so we have force A in the X direction, and then force A in the Y direction. Right. We have 50 newtons acting at the corner here. We have force B in the Y direction. Okay. And then we had 100 newtons acting 1 meter away. So again, this is 1 meter. Okay. So first thing, I'm going to do some of the forces in the X is equal to 0. This is equal to force AX plus 50. So that gives us force AX is equal to negative 50. That's good. Okay, and then some of the forces in the Y. We have force AY minus 100 from this plus force BY is equal to 0. And so then we need the moments to figure out the values. There's some of the moments. Let's see. We're not going to take it around. I guess it's probably best to take it about point A because that's where we have 2 reactions there. That would be the easiest place to take it around.
Right.
So we have some more moments about A. Let's see. And we'll do this as a vector. Okay, so that's equal to the 0 vector. Okay. So first one, we have, with this force, this is at a negative 6 j hat across 50 and an I hat that's in the positive X direction, but the distance is in the negative Y direction. Okay, and then with this force, that's 1 meter in the I hat direction, so plus 1 I hat across, and that's a negative 100 j hat. And then finally we have this force, which is just the, where did we say that was? 3 meters. Oh wait, I said this was actually, yeah, it's supposed to be 5 meters. Okay, so this was, it's going to be 3 meters away in the I hat direction, plus 3 I hat across, and then it's
Where did you pick your XY coordinates? Did you pick the upper left-hand corner for XY? Does that matter in this case?
Yeah, I guess I put it where I'm taking the moment about.
Okay.
So I mean, the main thing was that you have, we know that this is going to be the positive y, this is the positive x, and then for simplicity's sake, I put it at there. Technically, you could put it wherever you want. That's the most convenient spot to put it for coming up with the distance values. Okay. So 3i times force b and the y. Okay. So first thing, we have a j cross an I hat, which will give us a negative k hat. So let's see. Obviously, again, all of these are going to be in the k hat. Whenever you're dealing with moments in 2D, it's going to be k hat. So, but j cross I will give you the negative value. So because it's already negative, it becomes a positive. So it's positive 250. And then we have a 1 cross a negative 100. And that's I cross j is going to be positive k. So it'd be negative 100 there. And then 3i hat cross fby j hat is going to be a positive k again, so plus 3 fby, and that's equal to 0. So then fby is equal to, let's see, this is 150. If you take that to the other side, that's negative 150 divided by 3 is negative 50. And we're going to say our units were Newton meters. And then if you plug that, let's see, does that make sense? Actually, this doesn't make sense because I said there was a roller there. It can't be negative. So technically, this problem would be
Indeterminate?
I think it would actually be only partially constrained because technically the roller can't be pulling down there. So I guess when he was going over this problem, he just said it was statically determinate, but again, it also depends, I guess, on where you're saying the forces are. If you have a force here that's creating, are we creating a positive moment about this axis, whereas this can only cancel a negative moment. So if this were going the opposite direction, then this would be okay for resisting that, but in this case it's not. So we'll just say that's not possible. But if it were possible, you would just take this value and plug it back into your force equation to get the value there. I can just keep going over more review problems unless you guys have any more questions.
In a second.
Okay.
So let's get down. I really need to study determinate pressure control stuff.
Yeah. There were quite a few questions, like a bunch of people stayed after. I don't remember if either of you were there, but they stayed after to ask about, just making a slide here. There was a problem in class that he was talking about where it was a 3D pin here, where you have
That thing.
an angled one. I hope he doesn't actually put this on any of their tests because I looked at this for a while and I'm not sure how he got his answer. Because basically what he was saying was if you have a force that's sort of like coming out here, that's creating a moment which will cause this to bend, or it will cause this to move up, so it would be partially So let's just for a second here. I actually did work out some of this. But okay, so let's say this is the y-axis and this is the x. And then let's draw that over here. We're saying this is a 90-degree angle. So in this case, this is going to be the y, and this is going to be the x. Okay. So the problem is that with a 3D pin like this, it's not going to let it travel, but it can let it rotate about this axis, which basically means that it can do a moment, it can resist a moment going the y direction and the z direction, but not the x direction. And for this one, it's the opposite. It can let it in the x, but not the y. So when you're doing a force about here, what you're actually doing is you're creating a moment sort of about an axis up here. So let's just say this is the axis about which you're rotating. And that's, if you look, that's in the x and y. And so I think what he was saying was that because this one can only support a reaction, a moment in the y, and this one can only support an x, that they can't support that moment. But actually, because the combination of the two supports a moment in the y and the x, you're actually getting both of them. Although I would still say, I'm pretty sure it's statically indeterminate because there's not enough. You'd have to know this would actually bend, and you wouldn't be able to figure that out by a rigid form. So that was just an interesting problem. I'm not entirely sure if my answer is right. I know the other thing he was talking about after class was a problem kind of similar, where you've got, let's say like this. Again, this is a top-down view of what your pins look like. And in this case, since these are even with each other, if you put a force there, this is definitely going to rotate that way. Because these are each only supporting a moment in the y direction and not in their x direction. So if you have a moment here, that's creating a moment about the x-axis, and you can't support that with this. So it's just going to rotate. So that's just an interesting problem from the class. I could probably go over a few more problems from yesterday's class. We did one where you pin here, an angle beam. Okay. And then at this end, you have a wheel attached to the end. And this wheel is on an angle of 30 degrees. So I think part of the reason why this might be a little tricky is figuring out the direction that the force is going there. So let's just write in the rest of the problem. We had a 750 pound force. This was 3 feet away from this edge. And this is also 3 feet away from this edge. So the entire thing was like 6. We'll call this point A. This is point B. So one of the questions might be, how would you determine the angle that this force is acting at? Well, okay, so let's draw this out here. So we know it's going to be normal to this angle, or this plane here, which is at 30 degrees. So if we draw it like that, that's a right angle. So if we continue this line here, Now we have just a triangle, a right triangle here, and you see that this is 30. You can tell that this is 60. So that's one simpler way of coming up with it. We know the force then is going to be like this. Okay. So when we draw that reaction here, we're going to call that FB, and this is made up of components like this, FBX and FBY. So that's one easier way of coming up with that. And again, this is going to break down into, you can write this as FB, the vector, is equal to the magnitude of the vector times the direction here, which is negative cosine 60 plus sine 60. Sorry, this is negative cosine 60 in the I hat plus sine 60 in the j hat. Okay, so that's how you would write that vector. Now, we do the sum of the forces. It's equal to the zero vector. Okay. So actually, I forgot to do a free body diagram, so I should probably do that first. Okay, so we have FAY, FAX, and then we have that here, and so 50. Sorry, no, this was pound force actually. I'll just leave the unit off for now. Okay. So now to get some of the forces, we have the force of A in the x direction. Plus the force of A in the y direction. Minus 750 in the y direction, and then plus this entire FB here. I'll write that over here. Thanks for coming. Okay, plus sine 60 j hat. Okay, so that's the some of the forces here. So let's see. Okay, yeah, so that's equal to the zero vector. So you can take each component in the I and j direction. So in the I direction, we have FAX plus FB times negative cosine 60. So let's see. Okay, there. So FA X is equal to FB cosine 60. And if you look in the y direction, y minus 750 plus FB sine 60 is equal to 0. Now we have to look at the moments. Do that over here. And then again, because there's a pin here, there's two reactions, so it's probably best to take it about the pin or about the point with most reactions. Okay. So first one we're going to look at, we don't have to include FAX and FAY because they're at the pin, so if you're taking a moment about that, they're not there. So first one is the 750, which is 3 feet away in the X direction. So 3 I hat cross negative 750 in the J hat. Okay, and then the other one we had was the bowler is going to be 6 feet in the X direction and negative 2 feet in the Y direction. So we can write that one as plus 6 I hat minus 2 J hat. And then cross FB, which is that big thing we had up in the top right hand corner. I cross J is positive K, negative 2250, plus 6 FD sine 60. So that was from over here 6I times sine 60J. Okay. And then the other one from that was minus 2 FB cosine 60. And that's from negative 2 times negative cosine 60. But because J cross I, we still end up with a negative in the K. Okay. That's equal to 0, like I said. We go to new slide here. So if you go back for a second here. If you notice there's FB in both of these terms, so to get FB you have to factor it out. So first thing we do is we move the terms to the other side. So we had FB, so 6 FB cosine, so sine 60. Minus 2 FB cosine 60 is equal to 2250. After we move it to the other side, factor out FB, 6 sine 60 minus 2 cosine 60 2250. B, divide both sides by this term and you have your answer. Over 6 sine 60 minus 2 cosine 60. And this is equal to 536. I think that's right, 536.205, and the problem is given in pound force. So that's our first result. Now, if we go back and plug this in, we had, where's our equation with that? Okay, so we have FAX is simply FB cosine 60. Okay. Okay, so this is equal to 536.205 cosine 60, which is equal to 268.103 again in pound force. And then we had another equation which related all of these together. It related FAY to FB. So if we plug that back in, we have FAY equal to 750 minus FB sine 60. Plug in FB. And this turns out to be 285.632 pound force. So there's our three results here. So it looks like we're out of time for today. Thanks for coming. I hope you got something out of this.
Yes.
And I hope to see you next week.
All right. Thanks for your time. I was surprised not a lot of people showed up.
Yeah, I mean, I've only had a few people show up throughout the entire semester, so I'm just glad people are finally, maybe it's because your test is coming up, what is it, the 22nd?
Yeah.
Yeah, so next week, next week everyone will be here, hopefully.
All right, thank you. Have a good
Sure, you too.